Okay, this is page 15 of the synchronization notes, and section 6 is the dining philosopher's problem. And this was created by Edsger Dijkstra. That's the same Dutch computer scientist that invented semaphores, and I think that he created a min-path algorithm for the traveling salesman's problem. I might be a little off on that, but he did something like that. Anyway, smart guy, obviously. Created this problem for a grad exam. I think it was PhD students, and he wanted to illustrate a concurrency problem. And instead of phrasing it in terms of, I think it was 5 shared tape drives, he phrased it in terms of 5 philosophers sitting around a table eating spaghetti, but they're sharing forks with their neighbors. And it was to show, I guess, how you could deadlock, or to create an algorithm so that they don't deadlock. So let's draw the table here. And I'm going to put philosopher 0 here, and I'll try to distribute the other philosophers relatively evenly. Okay, so there's our 5 philosophers. I've numbered them from 0 to 4 because we're going to be using arrays, and so the philosopher number will be an index into that array. So in front of them, they have their bowl of spaghetti. That's about the limit of my drawing abilities right there. This problem is sometimes phrased using bowls of rice with chopsticks, which maybe makes a little more sense, but when Dijkstra set this up, he used bowls of spaghetti with forks. So we've got a fork placed between each philosopher, and just drawing them as kind of mini tridents. If you want, you can make a prettier fork. That last one's pretty bad. And I'm going to number these forks. So I guess I'm going to start to the left of philosopher 0, and that will be fork 0. And then going clockwise, fork 1, fork 2, fork 3, fork 4, and we've got fork 0. So most of the philosophers will choose, the fork on the right will be the same number as the philosopher, and then the fork to their left is the philosopher number plus 1, with the exception of philosopher 4, where the fork to their left is fork 0. Okay, so the philosophers alternately think and eat. So they think for a while, I guess that's hungry work, so then they decide they want to eat. So they try to pick up both their forks and eat for a while, and then they'll put them both down. And the times that they're thinking for and the times that they're eating for are unpredictable. So need both forks to eat, and the challenge was to design an algorithm such that no philosopher starves. And we also want to make sure that they don't deadlock, which would cause them to starve. So for the solution, or the implementation, I guess, this is going to be a programming implementation. The philosophers, they're actors, like they're actively doing stuff, so it makes sense that they will be tasks, whereas the forks, there are things that only one philosopher can hold at a time, or one task can hold at a time. So a natural representation for the forks is with mutexes. Okay, so we'll look at code for this on the next page.